Okay, section 4.4, optimization problems. Goals are listed. You can read those on your own time. Looking at the graph to the right here, for example 1, you'll see that this is a graph of f prime. So each of the output values are the slope of the graph for f. So let's look at part A. Find all x coordinates at which f has a relative max. Okay, so for part A, for f to have a relative max, f prime has to go from positive to negative. And the only location at which that does that, so here's f prime positive, here's f prime in red, you'll see f prime negative, and then here's where f prime equals 0. Therefore, there is a relative max located at x equals negative 2. Okay, for part B, we want to know on what open intervals contained in negative 3 to 4 is the graph of f both concave down and decreasing. So for the decreasing part, we want to know where f prime is less than 0, and for the concave down part, we want to know where the second derivative, f double prime, is also less than 0. So I'm going to highlight the locations where that happens. Of course, we know, so according to my sketch earlier, f prime is less than 0 anywhere the graph is red, and it will be concave down when the slope of f prime is negative. Therefore, that would happen on this interval and on this interval. So the function f would be decreasing and concave down on the interval from negative 2 to negative 1, as well as on the interval from 1 to 3. Alright, for part C, find the x-coordinates of all points of inflection for the graph of f. Give your reasoning. So we will have points of inflection. Points of inflection will exist where f double prime is equal to 0 and f double prime changes sign. Okay, therefore on this I see that f double prime would equal 0 at x equals negative 1, x equals positive 1, and x equals 3. Notice that as well, along with that, the second derivative goes from negative to positive at this point x equals negative 1, from positive to negative, and then from negative again to positive. So the points of inflection would exist at x equals negative 1, positive 1, and positive 3. Okay, in an example like this, find two non-negative numbers whose sum is 10 and whose product is a maximum. Okay, so the sum of the two numbers x and y equal 10. I'm going to solve for y and call that 10 minus x because I've got the product in terms of x. And therefore the product in terms of x would be x times the quantity 10 minus x. Alright, so let's expand that. So the product in terms of x would be 10x minus x squared. Just as a reminder, if I want to maximize something, a couple ways to find a maximum. I could find where the derivative is 0, and leading up to that from the left-hand side, the derivative is positive, that it's 0, and then it's negative. Or I could find where the derivative, right, I want to know where p prime of x equals 0 if p double prime of x at that point is negative, then I'm guaranteed a max. So check this out. I'm going to find the derivative and the second derivative. And let's compare some of this. So I get 10 minus 2x, and the second derivative would be negative 2. What this does is it guarantees me that the function is concave down everywhere. Therefore, wherever p of x equals 0, wherever p prime of x equals 0, then I have a maximum. So let's set 10 minus 2x equal to 0. It looks like x equals 5. If x equals 5, remember x plus y equals 10. Therefore, 5 plus y equals 10. Therefore, y has to equal 5. And if that's true, then the product would be 5 times 5. And so therefore, if those two numbers have to add to 10, then the maximum product would be 25. Okay, example number 3. Farmer Best has 10 meters of wire, which he's going to create a fence with. He plans to build 2 identical adjacent pens as shown. What are the dimensions of the total enclosure for which the area is maximized, and what is the domain? Okay, first off, we're going to assume that these two pieces of this these pens already exist. Maybe it's a concrete wall or something like that, or maybe a real steep hillside or something like that. Okay, so what we're going to do then is we're going to take and we're going to create these 3 lengths of fencing. We're going to call them X. We're going to create then these 2 widths, which we're going to call Y. And then what we know is that these have to add up to 10 meters. Okay, now it wouldn't make sense, right? If I had just 3 x's equal to 10, that would mean y would equal 0, therefore the pen would have no depth. So x has to be less than, right? X has to be less than 10 thirds. If x is less than 10 thirds, then we actually have depth to our pens. X also would obviously have to be greater than 0. So here's our domain for our function. Okay, but what we're trying to maximize is we're trying to maximize area in terms of x. So area of this in terms of x would be width times length, and the length is 2y. Alright, so here's our width, here's our length. If we find the area, we get 2y. Now if I were to use this right now, I'd have 2 variables, which would make it hard to differentiate and would get really complicated. So what I'm going to do is I'm going to solve for y up here. So I would subtract 3x, and I'd divide by 2. So it looks like the area with respect to x, we're going to do a little bit of simplifying here in a moment, would be 2x times y, and y would be 10 minus 3x over 2. I'm going to simplify off camera. Okay, so as I simplified this area function with respect to x, these 2's canceled out, I distributed the x, and I'm good to go. Okay, I'm going to do the exact same thing I did in the last problem. If a prime of x, since I want to maximize, equals 0, and a double prime of x is less than 0, then I'll have a maximum. That won't require me at all to test any other endpoints or anything like that. This is really sneaky and awesome, but it doesn't always apply. Okay, so the derivative a prime of x would equal 10 minus 6x. Okay, so if this equaled 0, then it looks to me like x would equal, what, 10/6, which is 5/3. Okay, now let's check the second derivative for a moment just to see if it'll always be negative. So I'm going to take the derivative of this to get the second derivative, which will give me -6. Since the second derivative is always negative, I know that when f prime of x equals 0, I'd have a maximum. So the area when x is 5/3 would equal 2 times 5/3. I'm taking this directly from here, right here, right? Or I could use this. but I'm going to choose to use this version. Okay, 2 times 5/3 times 10 minus 3 times 5/3 over 2. So I'll get 2 times 5/3 times 10 minus 5, right? These 3's will cancel, which will be 5/2. The 2's will cancel, and it looks like I get a maximum area of 25/3. What would that be? Meters squared, I think it is. All right, so that would be the maximum area when x equals 5/3. All right, a lot going on this page, so let's consider a triangle in the xy plane. 2 of the vertices are on the x-axis at 1, 0, and 5, 0, as shown here. And a third vertex is on this graph, the graph of natural log of 2x minus 1/2 x plus 5. Okay, so I just put a general sketch of this. I knew what it looked like. You may not, but you don't actually even need it. All right, so we want to maximize the area of such triangle. So if we had the point here, we'd have a triangle, right? If we had a point up here, we'd have a triangle all the way from, on this interval, from 1/2 to 8. Okay, so the area of a triangle is 1/2 base times height. Well, the base is always going to be 4, as shown below, and the height will be whatever the y value is if I plug in some x value. So what we want to do is we want to take the derivative, and we'll even take the second derivative and see if it helps us, but it may not. If the second derivative test doesn't help us, meaning that we can't confirm that the second derivative is always negative, then what we'll have to do is test critical points. Okay, so let's go ahead and find the first and second derivative. I'll do that off camera. Okay, so a couple of things that I had missing. I had forgotten an x here, and I actually simplified it by distributing what looks like a 2 over here to all these terms. And I get the derivative is equal to this, so I'm going to simplify that real quick because I forgot to do that. So that would be, looks like these two 2's would cancel, and I get 2 over x minus 1. That's our derivative. So if we want to know where that equals 0, right, we want to know where this equals 1, which clearly is at x equals 2. Okay, now the second derivative, right, the derivative of this would be negative 2 over x squared minus 1. Not real clear where that, if that would always be negative. Would it be? Yeah, it actually would be. Okay, so that would always equal 0, or always be negative, right? Therefore, what I could say then is, since f prime is equal to 0 at x equals 2, and I should call that a prime, and a double prime is less than 0 for all values on this, for all x on this interval from negative 1/2 to 8, right? Then, or from positive 1/2 to 8, sorry. Then there's a max, a relative max, let's say. Relative max at x equals 2. So all I'd have to do is plug 2 in to my area function, and we'd have an answer. I'm going to do that off camera. So I plugged in a 2. I plugged it in up here. Right, here's my area function. I plugged in a 2 here, got 4. I plugged in a 2 here, got negative 2. And so it looks like the area when x equals 2 would be 2 natural log of 4 plus 8. Let's see if we have that as an option on our, yes we do. Multiple choice, our answer would be C. Okay, so on this page we have a number of tips when working through this type of optimization problem. You can go ahead and pause the video and take a look at that. So that's 4.4 on optimization.